Okay, so we just got done in the previous few slides, the previous lecture, we just got done talking about elements, right, and atoms specifically, and what atoms were composed of, so the various subatomic particles of atoms, okay? So now in this last little bit of chapter 2, we're going to move into talking about compounds, okay? And so compounds are going to be things that are composed of more than one atom, right? And those compounds are held together by things called chemical bonds, okay? So there are two different types of bonds. There are ionic and covalent bonds, and we'll talk about the differences between them. But also important to note that these chemical bonds result in these interactions between the charged particles of the various atoms that we're making a bond with, right? So remember that our charged particles were our electrons, which are negative charged particles, and our protons, which are positive charged particles, right? And so what's making these bonds are the, let's say, atom number 1, the electrons of atom number 1 being attracted to the protons, of atom number 2, and vice versa, the electrons of atom 2 being attracted to the positively charged protons of atom number 2. Okay, so it's these guys, the electrons and protons, that are making up the attractions that lead to these atoms coming together and forming these bonds, okay? All right. And testing again, 1, 2, 3. So what type of bonds we have? So the first one we talk about are ionic bonds. And the most important thing to always remember with respect to ionic bonds is that they occur between a metal and a nonmetal. Okay, so if you have a metal and it's bound to a nonmetal, it is an ionic bond. Okay, so how do you know what a metal is? Well, you go back to the periodic table. There was that nice little stair step. Everything to the left of the stair step was a metal. Everything to the right was a nonmetal. Okay, so how do these ionic bonds actually form? So first off, what usually happens is there is a reaction where the metals, who like to give up electrons, give up some amount of electrons to the nonmetal, okay? So for example, if you had sodium is this nice, shiny, very reactive metal. It's a group 1, right? So it's an alkali metal. And you put it in the presence of chlorine, which is a nonmetal, okay, it's one of our halogens. Sodium loves to give up electrons, so it will give up an electron to the chlorine. In the process, it makes a positive charge ion, because it's only going to give up one electron. This is called a cation. And then the chlorine, by taking that electron, makes a negatively charged ion, which is an anion, okay? So that happens first. That transfer of electron happens first between the metal and the nonmetal. Then the bond that results afterwards is between the two ions that have formed from that transfer, right? So now we have a positively charged ion, we have a negatively charged ion, and these guys are attracted to one another, and that's what forms our ionic bonds, okay? Okay, so that's ionic. We have a metal with a nonmetal, and it's what results after the transfer of electrons from the metal to the nonmetal. The other type of bond that we deal with is a covalent bond, okay? And so a covalent bond, it occurs between two or more nonmetals, okay? So if you have two or more nonmetals, again, going back to that stair step, everyone over here is a nonmetal, then you have a covalent bond. Okay, so covalent bonds form because these nonmetals, instead of transferring electrons and forming ions, instead they actually share the electrons between the two things, between the two nonmetals, and that's how they form this bond. Okay, and so because of this, the things that result are called molecules. So if you have something that is a covalently bound collection of atoms, we call this a molecule. And because of that, anything that has a covalent bond tend to be called molecular compounds because they form molecules, so we call them molecular compounds, as opposed to ionic compounds, which result between a non-metal and a metal. Okay, so how do we represent these various types of compounds that can form? Okay, so we use what is called the chemical formula. Okay, so the chemical formula represents a few different things, okay? So number one, it represents the actual elements that are composing the compound, okay? And number two, it also gives us the actual number of elements that are there, okay? So for example, if I was going to write the chemical formula for water, I know that water is composed of hydrogen and oxygen, right? So I would represent those two things via their chemical symbol, and I know that there are 2 hydrogens for every 1 oxygen. And so how we denote that is we have a subscript denoting the actual number. So it's 2 hydrogen for every 1 oxygen. If there's only one thing, then we just leave that subscript alone because there's only one thing and it's kind of implied that there's only one, okay? So the chemical formula, which gives us the elements that are in the compound in their chemical symbols, as well as the relative numbers, that's essentially what is being represented when we put H₂O for water. There are 2 hydrogens for every 1 oxygen. Same thing for carbon dioxide. For carbon dioxide, the chemical formula is CHO2. That tells us that there are carbon and oxygen that compose carbon dioxide, and there are 2 oxygens and 1 carbon, okay? Same thing for sodium chloride, we represent it as NaCl. These are the chemical symbols for both sodium and chlorine, and they come in a 1-to-1 ratio. And then for carbon tetrachloride, it's carbon, and then there are 4 chlorines. So 1 carbon, 4 chlorines, that's what we mean by carbon tetrachloride. Okay, so these are all the chemical formulas for these various compounds that have been listed. Okay, so there are a couple of different ways that we can denote these chemical formulas. There are 3 different types of formulas that I'm going to introduce you to. The first one is called the empirical formula, the second is the molecular formula, and the third is the structural formula, okay? So these guys differ from one another based on the information that we have available about the compound, okay? And so we essentially go from the least amount of information up top, that's what the empirical formula gives us, to the most amount of information at the bottom. That's what the structural formula is going to tell us, okay? So what is the empirical formula versus the molecular formula? Okay, so the empirical formula for a compound is just going to give us the relative numbers of atoms that are present in the compound, okay? The molecular formula, on the other hand, is going to give us the actual number of atoms for each element that are actually in the compound, okay? So for example, for the difference between the two, for something like CFH or C4H8, this is the molecular formula. So this is the molecular formula. This is giving the actual number of things that are there. There are 4 carbons and 8 hydrogens, right? But this can be reduced down to give us the relative numbers of things, right? So both of these guys are divisible by 4. So 4 and 4. Actually, let me erase that. Get my eraser. This guy, this guy. So both of these guys are divisible by 4. So this can be divisible by 4 and 4. So this is carbon 1 H2. This is the empirical formula. This gives us the relative numbers of things, right? What this tells us is there, in this compound, there is 1 carbon for every 2 hydrogens, okay? So empirical formula is the reduced version of the molecular formula, if you want to think of it like that, okay? So for example, again, another one, B2H6, this is our molecular formula, right? If we want the empirical formula, again, it's going to be the reduced version of that, right? So both 2 and 6 are divisible by 2. So to get the empirical formula, I would divide by the whatever least number multiple or whatever it's called in math. And that gives me BH3. This is the empirical formula for this compound. Okay, and then for this last one, CCl4, right? This is the molecular formula. This is what it actually contains. It contains 1 carbon for every 4 chlorine. But is there any way that we can reduce this at all? No, right? So this ends up being both the molecular as well as the empirical, because this guy, these aren't reducible, but they're as reduced as they can be. So this is both the molecular and the empirical formula for this compound, okay? So empirical formula gives us the relative number, right? It's like the reduced version of the compound, whereas the molecular formula tells us the actual numbers of atoms or elements that compose the compound. Okay, so the last one is going to give us a little bit more information. Okay, so the structural formula gives us not only the actual numbers of atoms that are in a compound, but it also shows us how they're connected to one another, right? So for example, if we had something like hydrogen peroxide, so H₂O₂, right? This is the molecular formula. This is the actual number, so a molecular formula. If I wanted the empirical formula, right, both of these could be reduced to H and O. So this is the empirical formula. But again, when I write this, H₂O₂, does that give me any information on how these guys are actually bonded with respect to one another, right? The way I've written it, you could just assume, oh, well, H is bound to an H, is bound to an O, is bound to an O. But this is not correct. This is not actually how the atoms are bound to each other or arranged with respect to one another, right? This is actually how they are bound to each other. So you have a hydrogen that is bound to an oxygen that is bound to an oxygen, and another oxygen that's bound to a hydrogen. So again, this gives us the actual numbers, right? This tells you there are 2 oxygens and 2 hydrogens in this compound, and it actually shows you who's attached to who, and kind of also gives you an overall indication of the geometry with respect to one another, okay? So this is the structural formula for hydrogen peroxide. Again, it gives you the most information. It gives you the actual numbers, just like the molecular formula does, but it also gives you the actual attachment of atoms to each other, who's attached to who in the overall compound. Okay, so again, I've already said this at the beginning, but just as a reminder, you had 3 different types of chemical formulas, right, that I just introduced you to: the empirical, the molecular, and the structural. Of the 3, the structural gives you the most information. It gives you how many actual things are there. It gives you how they're attached to one another. Whereas the empirical, gosh darn it, this is irritating me. Whereas the empirical gives you the least amount of information. All it does is give you the relative number of atoms in the compound, and it gives you no information with respect to structure. Okay, so with respect to information, we go from least up here to most down here. Okay, all right, so this leads into this question, and I'm going to go ahead and put this question on the quiz. Okay, so in this question, I'm looking for which one of these 4 compounds, so you have a choice between A through D, has an empirical formula that is identical to its molecular formula. Okay, so it's going to be one of these. One of them has an empirical formula identical to its molecular formula. It's probably going to be the one whose molecular formula, which is given. I should note that these are all given. These are all the molecular formulas. It's probably going to be the one whose molecular formula cannot be reduced any farther. Okay, so formula. Too many words moving through my head right now. Okay, so we're going to start talking about how we can go about essentially categorizing different elements and compounds based on what they're made of. And this is going to lead us into kind of how we know what to name or how to call certain things. But we're going to start back by talking about elements just really briefly. And then we're going to move into talking about compounds again, okay? Okay, so it's important to note that we've been just kind of listing these atoms and elements based on just, kind of an idea that they're all like single atom structures, right? So most elements do exist in nature as just single atom structures. So these are what are called atomic elements. So what do I mean by that? So I mean like things like carbon, things like sodium, neon. If you went out and you found a sample of this element, right, so sodium, you would find it, or you could find it in its single atom form, right? Sodium is just an atom by itself. It's usually bound in a collection of other sodiums, but for the most part, we denote this as an atom, like a single atom, okay? On the other hand, there are a couple elements that are different from this, where you don't go out in nature and find them in their single atom forms, okay? These are what are called molecular elements. That was my eraser. So molecular elements, okay? So how do these guys differ? These guys differ in the fact that in their natural form, they're actually bound together with other elements of their same element or their same atom, okay? So what exactly do I mean by that? So for things like hydrogen, so hydrogen has a chemical symbol of H. You will never go out in nature and find a single hydrogen atom by itself, okay? Hydrogen instead exists as a diatomic substance, meaning you will only ever find it as an H bound to an H, right? We denote this as H₂, but in reality it's just a hydrogen that has a covalent bond with another hydrogen, okay? This is how you find hydrogen in nature, okay? Same thing for nitrogen. So nitrogen, you won't ever go out and be able to find a nitrogen just by itself. It comes in a packet of 2 as well. So nitrogen is always bound to another nitrogen. And then same thing with oxygen, fluorine, chlorine, bromine, and iodine. These are what we call molecular elements. Why do we call them molecular elements? Because they exist as molecules, because they exist being bound to their same exact atom via a covalent bond, right? So I talked about covalent compounds. We frequently call them molecular compounds because they're molecules. This is what we mean by molecular elements. They consist of being covalently bound to another atom of their same element, essentially, okay? So again, we have 7 of these guys that are diatomic, right? That they come in packets of 2. That's what we mean by diatomic. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. It's a nice little mnemonic to remember these because you will need to know these. You do need to know that hydrogen comes as H₂, nitrogen comes as N2, etc. What is it? Have no fear of ice cold beer. So no, I'm not going to write all that out. But have no fear, this is the H, no fear of ice cold beer, right? So it kind of gives you an idea of the various elements that come in diatomic form, okay? Okay, so another little thing to note that I am not super strict on, so I do want you to know these. You do need to know the 7 diatomic elements, but there are also 2 polyatomic elements. So phosphorus is a polyatomic element. It comes in groups of 4. So this is 4 phosphorus that are attached covalently to one another. And then sulfur is another polyatomic element. It comes in groups of 8, okay? These are not as important to remember, okay? Usually when we move on into chemistry, I will just write sulfur by itself and phosphorus by itself. But in reality, it is a polyatomic element. It comes as P4 and S8. That's how you would find it in nature. Okay, so we just talked about how elements can be either atomic or molecular, right? So most of the elements are atomic, meaning that they exist as single atoms, whereas 7 of them were diatomic. These were the molecular elements, right? Those are the ones that I listed. So it's the same type of things when we start to deal with compounds, right? So compounds can be classified as either ionic or molecular, okay? And again, it depends on the type of bond that is forming the compound. So the first one that we talk about is molecular compounds, and there's a reason why we kind of differentiate them between ionic compounds. Just as a reminder, how do you know if you have a molecular compound? How do you know if you have a covalent bond? Well, you have 2 or more nonmetals, right? So nonmetals, right side of the periodic table, always know it's on the right side of the periodic table, and it's multiples of them, then it's probably a covalent bond, it's probably a molecular compound, okay? okay? So we call these molecular compounds, and we say that they exist as discrete molecules because they do, right? So if something like, let's say a molecular compound would be something like CO2, carbon dioxide. When you go out and you look for carbon dioxide in nature, you will find individual carbon dioxide molecules, right? So this is carbon that has 2 oxygens, that's bound to 2 oxygen. So when you want to find carbon dioxide, you will usually find it like this, and it will be surrounded by other carbon dioxide molecules. That's what will make up the substance that you're dealing with, right? So what's important to note about these molecular compounds is that they tend to be either gases or liquids at room temperature, right? So their natural state tends to either be a gas floating around or a liquid, something like water, at room temperature, okay? And again, the basic unit of them is the compound. You can find the actual compound as written. So that kind of seems silly. Why are we stressing that? Well, it's actually different for ionic compounds, right? So for ionic compounds, again, this is going to be a compound that has an ionic bond. So how do you know if it has an ionic bond? It's between a metal and a non-metal, okay? But for ionic compounds, we tend to write them as if they existed as discrete units, right? So if we wanted to represent something like sodium chloride, we would write NaCl, right? That's how we write our chemical formula for sodium chloride. And when you look at that, you think, oh, yeah, so we must be able to find in nature a sodium and a chlorine by themselves, just existing like that, right? But that's kind of inaccurate. So what this guy is called the formula unit for this ionic compound, and what it is defined as the smallest electrically neutral collection of ions in the overall compound, right? But in reality, for sodium chloride, you will never just find a sodium and a chlorine by themselves, isolated, ever, right? Instead, what they form, these ionic compounds, they form these large, like lattice or large crystal type structures where you have the sodium and it's surrounded by the negative charge chlorines, and a sodium surrounded by the negative charge chlorines, right? And so we represent this real structure by the formula unit, right? Again, which is just going to be the smallest electrically neutral collection of ions. So if sodium, remember, had a +1 charge and chlorine had a -1. So to make those guys electrically neutral, you would need a 1 sodium to 1 chlorine. That's what we mean by the formula unit. But in reality, again, this is what you're going to find, right? And so for ionic compounds, as opposed to the molecular compounds, if you look at this thing, right, this big chunk of stuff, this is not going to be a gas at room temperature, right? This is usually not going to be a liquid at room temperature. So these guys tend to form solids as their physical state at room temperature, right? So ionic compounds tend to be solids, usually when, we're just looking at them and finding them naturally in nature. Okay, so then there's one last little bit, right? So those were molecular compounds. You actually find them as their discrete molecules. You have ionic compounds, which you won't find as a discrete molecule, but you do find in this large collection of ions, essentially this large lattice. And then we have this last little bit, which is called a polyatomic ion. So this is kind of like a combination of the two things that I just introduced, right? So a polyatomic ion is something where you have multiple atoms that have formed covalent bonds with one another, right? And as a collection have lost or gained an electron, okay? So what do I mean by that? So something like NO3 minus, so this is called, so this is called nitrate. This is the nitrate polyatomic ion. If you look at these guys, nitrogen and oxygen, what type of bond is forming this compound, right? Nitrogen, oxygen, both of these are non-metals, right? And so this is a covalently bound molecule, covalent bond, right? But together, as a covalently bound molecule, they have taken on an extra electron, right? So they have formed an ion. okay? So polyatomic ions are themselves molecular compounds that have either lost or gained an electron and formed an ion, okay? So this guy is nitrate. We call this one CO3 2-. This guy has gained 2 electrons, that's why it has a 2-. We call this carbonate. And this guy down here, ClO-, this is called hypochlorite, okay? Okay, so with respect to these polyatomic ions, again, all of these guys are negatively charged ions. These are anions. And so they are going to form together ionic compounds, right, when they bind to a metal. So these are going to form ionic compounds when they form a nice ionic bond with whatever metal is around them to form an ionic bond with, okay? Okay, so how are we going to know? So let's go back to ionic compounds. So given a compound, how do we know what the actual chemical formula is? Okay, so just as a reminder, metals like to lose electrons, right? Things on the left-hand side of the periodic table like to lose electrons and in the process form cations or positive charge ions, whereas nonmetals, things on the right-hand side, like to gain electrons and form anions or negatively charged ions, okay? For a lot of the metals, right, there are 2 columns specifically, 3 columns kind of, if you include group 3, we can predict the charge of the metal, right, just based on its position in the periodic table. And for nonmetals, these can also be predicted based on their position in the periodic table. So what am I meaning by that? We're going back to this idea behind ions, right, and how depending on the position for some of these guys, what charge they were going to form to get the same number of electrons as their nearest noble gas, right? So for example, we have, makes me mad, we have lithium here, right? Lithium is one of our group 1. So this first column is always called group 1, is our alkali metal. And to get to its nearest noble gas, which would be helium up here, it needs to lose 1 electron, right? So we need to lose 1 electron to get to this nearest noble gas. We know that lithium will always form a +1 charge, right? And for everyone in this column, this is what we mean by predictable, everyone in this column needs to do the exact same thing. They all need to lose 1 electron to get back to their nearest noble gas, so they all have this +1 charge, right? Same thing for this group 2. These are the alkaline earth metals, so group, oops, that's ugly. So same thing for these guys, group 2. These guys, instead of losing 1, need to lose 2 to get back to their nearest noble gas. They're always going to have a +2 charge. So group 1 is always going to have a +1, group 2 +2, right? If we go over here to the nonmetal portion of this, we know that the halogens, to get to their nearest noble gas, need to gain 1 electron, so they're always going to have a -1 for this group 6A. So just as a reminder, the halogens are group 7, whereas things like oxygen, sulfur, selenium, these are group 6. They always need to gain 2 electrons, so they're always going to be a 2- charge, okay? And going on to nitrogen, going on, etc., etc. All right, so these are the ones that we can predict. So how are we going to chart? Magnesium is in group 2, right? So it needs to lose 2 electrons. Realize that to be able to know the formula of a compound given whatever elements make up the compound, right? So let's say that we wanted to determine what the formula unit or the chemical formula was going to be for something that forms, for some compound that formed between magnesium and chlorine, okay? So magnesium, if we go back to our little ion, so we know that magnesium is always going to form a 2+ ion, right? A 2+ cation, whereas chlorine, again, if we go back to the previous chart, I bet that messes things up. So if we went back to the previous chart, which you can do, chlorine would want to gain 1 electron, right? And so it's going to form the Cl1- anion, okay? So now, when we bring these two guys together, we want to form an electrically neutral compound, right? We want to form something that has an overall charge of 0. So we need to combine these guys in some sort of ratio that's going to do that, right? So if chlorine is only a 1-, how many of chlorines do I need to balance this 2+, right? So hopefully you should be able to see for every 1 magnesium, I need 2 chlorines, right, to give me this overall charge neutral, because I have a +2 from this guy, so I need 2 -1s to give me a charge of 0, okay? So this is how, given whatever type of atoms are going in to make this ionic compound, this is how you could know what the formula unit or the chemical formula, whatever you want to call for this, is going to be. You need to combine these guys in whatever ratio to get this overall charge neutrality, okay? So we could do the same thing for something like, let's say, aluminum and oxygen, okay? So what kind of compound, or what is going to be the chemical formula of the compound that forms between aluminum and oxygen? So for aluminum, this is a group 3 element. It needs to lose 3 electrons to get to its nearest noble gas. So aluminum is going to have a 3+ charge, whereas oxygen is a group 6 element. It is going to gain 2 electrons to get to its nearest noble gas. So we could predict it to have a 2- charge, right? So now the question is, what ratio do we need to combine these guys in to get an overall charge neutral species, right? So for aluminum, we have a 3+, oxygen, we have a 2-, so we can't do like a 1-to-1 or a 1-to-2, but their nearest number multiple, right, is 6. Both 3 and 2 go into 6. And so we're going to combine them in that fashion. So how many times does 3 go into 6? So aluminum is going to give us a 2. And how many times does 2 go into 6? We need oxygen 3, right? So we have 2 times a plus 3, plus 3 times a -2. This is +6 plus a -6 gives us overall charge neutrality, okay? Another very easy way to do that is if you took this guy's charge, note that it becomes the subscript for the other thing, right? So oxygen's 2- charge, aluminum needs 2, whereas aluminum's 3+ charge, oxygen ends up needing 3. So you can take the charges and you can essentially flip them for the subscripts of the resultant chemical formula. If you looked up here too, with magnesium, same thing occurred. This guy goes down here, and this guy becomes a 1 as well, okay? Or you can just go back to, I need a charge neutral species. How can I combine these guys to give me that? Okay, so moving forward, we're going to start naming ionic compounds. So ionic compounds kind of have the more rules with respect to how to name them. And so what do I mean by naming? So let's say if I'm given a formula, let's go back to magnesium chloride. How do I know what to call this, right? How do I know it's magnesium chloride? I keep using that, but what are the specific rules with which I can take a formula and give it its appropriate name? So this is what we kind of call chemical nomenclature, and that's what the last little bit of this chapter deals with, okay? So we do start with ionic compounds because, again, they have more rules overall, and they're kind of harder to remember. So there are 2 different types of ionic compounds. There's what we're going to call a type I compound, type I, and a type II compound. So type I versus type II. And how do they differ with respect to one another? So the first type, type I, are going to be ionic compounds that have a metal that forms only one type of charge, right? So these are going to be our predictable main group metals. So predictable metals, whereas group 2 are going to be metals that form more than one type of ion. So they can be like a +1 and a +2 depending. These are going to be less predictable. These tend to be things like transition metals. Transition metals. Okay, So we're going to start by talking about type I predictable metals. Okay, so what are these type I predictable metals? So number one, there are main group metals that we've kind of mentioned previously. So this is group 1 and group 2, as well as aluminum, which is in group 3, which we've talked about, as well as a few of the transition metals. So these are kind of more rare. So zinc is one that is a transition metal, but it only forms a 2+ charge. Cadmium is another, it only forms a 2+ charge, as well as silver. Okay, so the majority of these guys up here, these are the predictable metals, are group 1, group 2. There is a group 3 in aluminum, and then just a few of the transition metals. So how do we name these type I metal compounds, these type I ionic compounds? Okay, so the first thing that we're going to do is we're just going to write the name of the metal. Okay, so whatever metal you're dealing with in the compound, you write the name of the metal, and then you're going to write the base name of the nonmetal, right? So the base name of the anion, and then you're going to end it with IDE. Okay, all right, so what are the various base names of the anion? So I've given you here a couple of anions. So I've given you like fluorine, chlorine, bromine. These are just a select few, and they've given you the base name for each one. So fluor, chlor, brom, iode, ox, etc. Okay, so when we're naming these ionic compounds, you're always writing the base name, and then at the end, you're writing IDE to the end. So when you do that with something like fluor, this turns into fluoride, chloride, bromide, iodide, etc. Okay? Okay, so let's utilize that, right? So we've got KCl. So what is the chemical symbol K stand for? So this is potassium. So this is the name, potassium. I just write the name of the metal plus the base name of the nonmetal. So this is chlorine. So base name is chlor, and then I end it in IDE, right? So how do I name this type I super predictable metal compound, this ionic compound? I write the name of the metal, potassium, base name of the nonmetal, base of non, and then I end it in IDE, okay? So potassium chloride. Same thing here. I have to recognize that Ca is a metal, it's calcium. So I just write the name of the metal, I put a space, I write the base name of the nonmetal, this is oxygen, so its base name is ox, and then I end it in IDE. So this is, what is the name of this compound? CaO, this is calcium oxide. And same thing for this last one, this guy Mg, this is our metal, it is magnesium. And then I've got my nonmetal here. This is bromine, so the base name is brom. And so then after I write the base name, I just finish it with IDE. So the name of this compound is magnesium bromide. So magnesium bromide, calcium oxide, potassium chloride. Okay, again, these metals, which are always listed first in a compound, I should have noted that, these are all predictable. Predictable. They all form only one type of charge. Potassium will form a +1, calcium forms a +2, or 2+, pardon me. Magnesium forms a 2+ as well. Okay, so we know that these are the type I ionic compounds. Okay, so what about type II? That's kind of the big question. What is type II? So these guys are these non-predictable metals, right? And so the big difference here is that it's not necessarily that they're not predictable, it's that they can form more than one type of charge, right? So for example, iron, so iron has the chemical symbol Fe. Iron can lose 2 electrons or it could lose 3 electrons, right? So if it loses 2 electrons, it forms iron 2+, and if it loses 3 electrons, it forms iron 3+, right? Both of these things are possible. So it wouldn't be correct for us to say something like, oh, the name of this compound is iron bromide, because that doesn't tell us what the charge is here. Like if I said, oh, I'm going to use iron bromide in my reaction, well, is this FeBr2? Oops. Is this FeBr2 or is this FeBr3, right? These are two entirely different compounds, and that's why we kind of have to specify, well, which one are we dealing with? Is this Fe2 plus or is this Fe3 plus, okay? And so to do that, when we're naming these type of compounds, what we'll do differently is we will write the name of the metal, right? So this would be, let's say we were doing something like FeCl3. So I'd write the name of the metal, iron, and then in Roman numerals, in parentheses, I would specify what the charge is of the metal, right? So this is iron 3 plus, so I would write that as a Roman numeral in parentheses. Oops, 3, right? So this guy, let's make it look like a Roman numeral. So iron 3, and then everything else is the same. So I would write the name of the metal, the charge of the metal as Roman numerals in parentheses, and then the base name of the nonmetal. For this guy, it's chlor, and then I end it in IDE, right? So this ends up being iron 3 chloride, okay? And it helps me specify again which ion am I dealing with when I'm dealing with iron. So what if we were to give you, instead of giving the name, what if we were to give you the charge, or the chemical formula? How would you be able to deduce the charge of the metal from this, okay? So just looking at this, if I wanted to name it, I know that this metal, Cr, is chromium. So chromium is what I would write first. So chromium, right? But then how do I know the charge right now? How do I know if this is +2 or +3? So usually the big indicator is going to come from the nonmetal, right? Bromine is a halogen, right? So for one bromine, you get a -1 charge. If there are 3 of them, that gives me a 3- overall. So chromium has to be a +3 to balance that 3-, right? It's the nonmetal that's going to tell you the overall charge of the metal. So this is chromium 3 plus. So I can write that here, 3 plus. And I'm going to write that 3 as parentheses, Roman numerals, chromium 3. And then same thing, I use the base name of the nonmetal and I end it in IDE. So same thing for this guy, I just did this one. So this is Fe is iron. So I'm just going to write the name of the metal, iron. Again, chlorine is another halogen. So 1 chlorine forms a -1. If I have 3 chlorines, that gives me a -3 overall. So this iron has to be a 3 plus to balance the 3- coming from these guys, from these 3 1-. So this is iron 3, and then base name of the nonmetal is chlor, end in IDE. Okay, so this one's a little bit same. It's the same concept, but it's a little bit different. Right now I have copper, and I have 2 of them, and with an oxygen. Again, oxygen is going to be the thing that's going to tell me the charge on the copper. Oxygen forms a 2- charge, okay? So if I have a 2- from my oxygen, and I have 2 of these coppers balancing it, then both of those coppers have to be a +1 charge, right? So if I have 2 +1s plus my 2-, this is for my coppers, this is for my oxygens, then I get overall net charge of 0, okay? So I have 2 coppers balancing this charge, so this has to be copper +1. So the name of this is copper, and then Roman numerals 1, and then oxide. Base name of nonmetal, end it in IDE. Okay, so a couple of things to note here, over here on this chart. Most of the transition metals are going to follow this. These guys are going to be type II binary compounds, but there are a couple of the ones that I've talked about in the main group that are also like this. So just be aware that things like mercury, lead, and tin, these guys are also more main group type metals that form more than one type of charge, right? So you don't necessarily need to know what type of charge they form. That's not important. But just note that you would have to use this naming scheme. Again, that differs in the fact that you have to specify the charge in Roman numerals and parentheses for these types of metals when you're naming them, okay? Okay, so I'm going to go ahead and stop this here. I'm going to put all 4 or all 3 of these. I want the correct name. I've given you the chemical formula. I want you to write the name correctly in the answer. And these will all be on the quiz on Blackboard. So this one, I think there was a problem back there where I had to identify the chemical one that had the same empirical formula as well as molecular. And then there's probably something else in there, but I've forgotten at this point in time. But all of these guys, their correct names are expected on the quiz. So for today, what we're going to do, I'm going to talk for like 30 minutes going over the final rules of chemical nomenclature that you guys should know. And then I'm going to hand out the activities and let you guys do that for the remainder of the time, okay? So hopefully you did the reading or the video assignment before you came to class. So you watched the video I posted, you took the questions, or you took the quiz, you did well on that. Hopefully also you did the homework that was due over the weekend. So that was Chapter 1 homework. I will post Chapter 2 homework within the next day, so I would look out for that. And I'll post an announcement on the Blackboard site when I actually do post Chapter 2 homework, so you guys can get started on that. And just as a reminder, we will have an exam coming up in 2 weeks. So our first exam is going to be on the 20th, which is a Thursday of September, and that's going to cover the first 3 chapters. So we're about to finish Chapter 2. We're going to start on Chapter 3. It's going to take us a little bit because it goes over quite a bit of information, but then we will take exam number 1 after that, okay? I should also note that with respect to exams, I will give you, I don't do study guides, but I do practice exams, okay? So for exam number 1, I will put up an exam from previous years that I've given, similar time frame, similar material, and I will give you the key to that as well, okay? So just to give you an idea of things that you need to be able to answer questions for, etc., okay? Okay, so in the video, I was talking about naming things, right? I was talking about naming ionic compounds. And there were 2 different ways that you essentially needed to utilize to name ionic compounds depending on the type of metal that you were looking at, okay? So there were Type I metals and there were Type II metals. And how do they differ from one another? Type I metal, was its charge predictable? Yes, right? So because of that, we didn't have to specify the charge on a Type I metal ionic compound, right? Type II metals, though, those charges were not predictable. So how did we specify the charge of the metal in Type II metals? We named them Roman numerals in parentheses, okay? So that's what the video assignment essentially went over. So we're going to pick off where I left off with respect to that, okay? All right, so the types of compounds that we were naming with respect to the Type I and Type II were what were called binary compounds, okay? So binary compounds is what I went over in the first few different types of rules, okay? And what those refer to, what binary refers to, is that for these guys, we were dealing with a metal plus one other type of element, okay? So it could be multiples of that, but it was only one other element as the non-metal. Okay, so now I'm going to introduce you to how to name ionic compounds that contain a polyatomic ion as opposed to just one other type of element, okay? So, what are polyatomic ions? I did go over this in the video. These guys are covalently bound molecules, right? Things like NO3, NO2, etc. But what has happened to them as a cluster of covalently bound things? They have either lost or gained an electron, right? So we have something that has a covalent bond. Man, my day is not good. Covalent bond. But as a whole, as a unit, they have either lost or gained an electron, so they've formed an ion, okay? So together, they have formed an ion, okay? So when we name these types of compounds, these types of ionic compounds, we are again going to write the name of the metal, depending on whatever the name of the metal is, and then we are just going to name the polyatomic ion, Okay, so with respect to the binary, we always said the base, and then we ended it with IDE. But now for polyatomic ion compounds, we're just going to write the name of the metal plus the name of the polyatomic ion. Okay, so for example, this compound, to name this, to give it its correct name, I would write the name of the metal. So what is the metal here? This is sodium. I do not have to specify the charge because it is a type I metal, right? And then I'm just going to write the name of the polyatomic ion that it's bound to, which is this guy. This is NO3 and has a 1- charge. This is called nitrate. So nitrate. Okay, so that's how I would name a compound, a metal ionic compound that contains a polyatomic ion. Same thing for this guy down here. I've got copper. And then this thing is another polyatomic ion. This is SO4 2-. That's the charge on it. This is sulfate. So for this one, what type of metal is copper? Is it type I or type II? Type II. So I would have to specify the charge on copper. If SO4 has a 2- charge, then what is the charge on that copper metal? It's a +2, right? So this would be copper with a Roman numeral 2 in parentheses, copper 2, and then just the name of the polyatomic ion, sulfate. Copper 2 sulfate. Okay, so that's nice, that's easy. The only problem is, how am I getting the names of these polyatomic ions? How do I know that this is nitrate, that this is sulfate, etc.? So there are a couple of different tricks that you guys can utilize to know these, but long term, what it's going to come down to is that you just memorize them, right? I know what nitrate is because I've seen nitrate thousands of times before. Similar type thing, you guys will just have to know the names of these polyatomic ions, okay? So I give you a list here, and I'm going to go through which ones are kind of important that you should focus on, but it's important to note that you not only need to know the name of them, you need to know their chemical formula as well as their overall charge, okay? So a couple of the polyatomic ions that I think are important are acetate and carbonate, as well as this nitrate-nitrite series, as well as these guys over here, not the permanganate. So the hypo all the way to per with respect to the chlorates, and then also sulfite and sulfate, okay? Also one more, sorry, phosphate. These are things that are kind of important later on, so it's important they actually do know the charge of some of these, as well as their chemical formula and name, okay? So if I were focusing on stuff, I would be focusing on these. But what's great about this is, does this require like any conceptual understanding of this at all? All it requires is a flashcard and memorization, okay? Okay, so I will show you one trick with respect to helping out on some of these. So notice that between nitrite and nitrate, so this guy NO2- is nitrite, NO3- is nitrate. What is the difference between these two? Nitrate has one more oxygen than nitrite, okay? If we go over here to all of these guys with these chlorines and oxygen, what is the difference between each of these individual polyatomic ions? Same thing. Everyone just has one more oxygen than the one above it, okay? So these guys are what are called oxyanions, okay? And so with respect to oxyanions, there are a couple of various tricks that you can utilize so that as long as you know one of the series, you can figure out the other one, okay? So oxyanions, again, are these polyatomic ions that have an element and it's bound to a certain number of oxygens. That's all they differ with respect to one another. They all have the same charge and they're all bound to that same original element, okay? So there are two different types of oxyanions. The first one is the type that has only two polyatomic ions in this series. Okay, so for example, this would be something like nitrate and nitrite. For this group, there's only two of them there, right? Same thing for sulfate and sulfite. There are only two oxyanions that have nitrogen and oxygen in some combination, okay? So for these, what's helpful to note is the polyatomic ion that ends in 8 always has the most oxygen, okay? For the group of oxyanions that only have 2 in the series, okay? So nitrate is NO3-. If you know what nitrate is, you can always figure out what nitrite is in the fact that it always has one less oxygen than the 8. Okay? So if I have memorized what nitrite is, NO3 1 minus, I can figure out what nitrate is. Oh, pardon. Oh, gosh. Okay. If I have memorized what nitrite is, okay, sorry. If I have memorized what nitrate is, then I can always figure out what nitrite is by knowing that it has one less oxygen than 8. Okay? So nitrite is NO2 1 minus, nitrate is NO3 1 minus. Okay? Again, they all have the same charge with respect to the overall charge of the ion. Same thing for sulfate and sulfite. If I memorize sulfate, I know that sulfite just has one less oxygen than that. Okay? Okay, so that's groups that only have 2 of the oxyanions in this series. There are clusters that have more than 2 of these polyatomic ions in this series. Okay? Their names, though, again, can be derived from the name for whatever the 8 is. Okay? So if you remember, or if you memorize what chlorate is with respect to these polyatomic ions, then again, what would chlorite be? So if I memorize that chlorate is ClO3 minus, how could I figure out what chlorite is? One less oxygen than 8, right? So chlorite is ClO2 minus, okay, or ClO2 minus up top, right? Then what we use are these little prefixes, okay? So per means one more, okay? So perchlorate is one more oxygen than 8, okay? So again, if I know chlorate and I have perchlorate, I know it has to have one more oxygen than whatever the 8 was. And then hypo as a prefix means one less than, okay? So hypochlorite is one less oxygen than whatever the ite was, okay? So if you memorize chlorate, you know that chlorite has one less oxygen than that. Hypochlorite has one less oxygen than chlorite, and then perchlorate has one more oxygen than chlorate. So my recommendation would always be to know what this guy is. You can figure out the rest from that. And again, these guys don't differ with respect to charge. They all have the same 1 minus charge, so they're all going to have the same charge in this series. Okay, so that's nice. That's helpful. Let's go ahead and utilize that and do a question, okay? So at this point in time, what you should note is how to name type 1 and type 2 binary ionic compounds, and also how to name ionic compounds that contain polyatomic ions. All right, so go ahead and give this question a try. So in this question, I give you the name of the ionic compound, and then I want you to write the cation, specifically the cation formula, the anion, and then the overall formula for the compound, right? So for example, I'll go ahead and do the first one. We have calcium fluoride. And so this is a type 1 ionic compound, right? Calcium is in group 2 on the periodic table. It always has a 2+ charge. And calcium is the cation here, right? Cations are the positive charge ions, where the anions are the negative charge ions. So the metal, the cation is calcium. So we'll go ahead and write the chemical symbol for calcium, but I'm wanting to write the actual cation, the ion form of this. So it's not just calcium, but calcium specifically, because it's in group 2, loses 2 electrons, so it takes on that 2+ charge. And again, you guys can go back to the periodic table where it gives you the various charges for the various ions that form, or you can just figure it out just from the position based on the periodic table. Second, fluoride. This is our nonmetals. This is our anion. It's going to gain electrons. And fluoride, because it's in group 7, just needs one more electron. So our anion here is fluoride -1, because it gains one more electron to get to the nearest noble gas. And so now, when I have my calcium, I have my fluoride, we're going to write the actual chemical formula for these two. And again, we're going to combine them in a ratio that's going to produce a charge-neutral compound. So because calcium is a 2+ charge, right, so we have a 2+ here, and fluoride is only a 1-, we're going to need 2 of these guys to give us our overall charge-neutral compound. So we've got calcium, and then fluoride, but if I need 2 of something, I can't just write 2 anywhere. I specifically have to write it as a subscript below the fluoride. So 2 fluorides, which are -1 charge, with 1 calcium, which is a +2 charge, gives us an overall charge neutral compound. And again, if you want to use the trick that I showed, probably when you have calcium, you have fluoride, these are the actual charges. If you just switch the numbers, put those in the superscript, that will give you the correct answer. And I don't like that, it makes it ugly, so we're going to go with it. Okay, so go ahead and try these and then come back. I'm not going to go through them, but I will give you the correct answers. Note that this is going to be a mixture of compounds that are metal and a non-metal, as well as compounds that are a metal with a polyatomic ion. So some of these are polyatomic ions. Also note that they're also a mixture between type 1, things like what I just did, things like calcium, potassium, as well as type 2 metals, which are these unpredictable ones that we have to specify the charge. So go ahead, give us a try, and then come back for the answer. Okay, so hopefully you pause it before you can see everything, but I've given you guys the answers here, where I've written down the metal and the charge on the cation column, the anion column, which is either the non-metal or the polyatomic ion, its charge, and then the charge neutral chemical formula for all of these guys are listed over here. I'm going to skip ahead to this one, and I'm going to put this on Socrative. So I provide you the formula, and I want you to type in the name, okay? If you want to get like a good green box and everything, make sure that everything is lowercase, and make sure there is a space where there needs to be a space in between words. So write everything in lowercase. Okay, so most of you guys did pretty good on this. Going through these, again, you have to keep in mind type 1 versus type 2 metals, and then you have to know the overall charge with respect to polyatomic ions, as well as just binary single elements by themselves. Okay, so on this first formula that we have, MgCl2, is this a type 1 or type 2 metal? Type 1, right? Super predictable. Magnesium, it's group 2. So magnesium, and then I don't have to specify the charge because we already know it. And then what should I begin with respect to the non-metal? Base name of the non-metal, this is chlorine. So we have chlor, and then what do I end it in? IDE. Okay, magnesium chloride. Same thing for the second one. Is this a group or type 1 or type 2 metal? Type 1, so sodium, predictable, has a +1 charge. What is this polyatomic ion? Carbonate, right? And so with respect to polyatomic ions, you just write the name of the polyatomic ion. You don't have to worry about the IDE. Same thing for this one. What is this polyatomic ion? OH. This is hydroxide. That should have been another one that I mentioned. You should know what hydroxide is, but you will later on because it's important with respect to acid-base chemistry. So this is calcium hydroxide. What about this guy? CuCl2. So this is a type 2 metal, right? We can't predict the charge of the copper just by looking at it. So to specify that, we have to say what charge it is. This is, what is the charge of copper here? This is 2+, so this is copper 2. And then base name of nonmetal, chloride. What about this guy? This is kind of a weird one. This is the only positively charged polyatomic ion. Okay, so there's only one positively charged that you guys need to know. This is ammonium. And then the second one, NO3-, is nitrate. And then this last one, FeNO3. What is the charge of Fe? Who is Fe? Iron. So iron, and then what is the charge here? 3. And then nitrate again. So NO3 has a 1- charge. There are 3 of them, so this guy has to be a +3 because of that. Okay, so that's, again, kind of, yes, go ahead.
So in the last one, it was, I got it wrong because the nitrate and the answer they gave us was nitrite.
Oh, my bad. It doesn't count against you in Socrative. I'm just looking for participation, but this is nitrate, so I must have typed it in incorrectly in Socrative. Yes?
In Socrative, it was NO2
Oh, yeah. So, sorry, sometimes these get mixed up when I type stuff in. We all make mistakes. And it's not going against you. So yes, in Socrative it was listed as nitrate, or nitrite, but here I have it as nitrate, so we'll just go with it. Okay, so moving on and specifying this, what we will utilize when we are naming molecular compounds is prefixes, okay? And the prefixes are going to tell us how much of whatever element we're dealing with we have, okay? Okay, so what are the prefixes that we use for things we have to talk about, and then we'll do the activity. So that was all with respect to ionic compounds, right? Ionic compounds are between metals and nonmetals, so we have charges that helps lead us in the naming. What about molecular compounds, though? What are they made up of? Molecular compounds, they consist of covalent bonds, right? So what type of elements make up covalent bonding? Metals? No, right? So what are molecular compounds made up of? Nonmetals. So it's a nonmetal plus a nonmetal. How do you know you have a molecular compound? Because you have a nonmetal bound to another nonmetal, okay? So because of that, we don't get charges, right? With respect to ionic compounds, the charges help us name or know what type of compound we're dealing with coming from the name, okay? We don't get charges in molecular compounds. And also, another issue that we run into is that any two elements can form a variety of different type of compounds, right? So for example, nitrogen and oxygen, they can combine to form NO, they can combine to form NO2. There are a variety of different things, right? So we couldn't just call one of them nitrogen oxide, okay? So to help us, molecular compounds, so you guys should know these. And for the most part, they're kind of already nice and laid out for you, right? So if you have one thing, the prefix you use is mono, two things, the prefix you use is di, tri, tetra, so on, all the way to deca, okay? So that's if you have 10 various things. So how we're going to utilize these prefixes in naming these molecular compounds is we are going to list the prefix for the name of the first element, okay? So prefix, name of first element, space, prefix, base name of second element, followed by IDE, okay? So for example, if we are naming this guy, what is the first element that is given in the formula? Nitrogen. How many of them are there? Two. So if I'm going to denote that, I have to say di, because that's the two prefix, dinitrogen. And then what is my second element? Oxygen. How many of them are there? Four. Four corresponds to tetra. Tetra, and then we just say the base name of the second element ending in IDE. So the base name of oxygen is ox, and then I'm just going to end it in IDE. So one thing to note, with tetra, we end in A. With oxygen, we start in O, right? That's two vowels. We usually don't like to do that. So with respect to something like this, we tend to get rid of the A. So this would end up being tet ox, and then IDE. So prefix, element, first element, and then prefix, base name of second element, ending in IDE. So what would this guy be? NO. How would I name that? So if we have only one, what do we say? It's mono, okay? But for these guys, if there's only one for the first element, we can always just omit the first mono, okay? So we don't have to say mononitrogen. We can just say nitrogen. And the mono is implied, but then I do have to specify how many I have of the second one, right? So what would I go with here? So this would be mon, and then again, I don't want to follow with two vowels, so I'll drop one of the O's, mon, ox, and then ending in IDE. Okay, so this one, because again, we don't have charges, we have to specify how much of each element we have. We do this with these prefixes, and again, you should be familiar with all of these prefixes. Okay, all right, so one more thing. This was molecular compounds. There's one more little... Okay, so go ahead and give this one a shot. So I've given you the chemical formula for these molecular compounds, and I'm wanting you to write out the correct name for them. And again, keep in mind that these are molecular compounds. They're covalent bonds, so these are two or more nonmetals. and you're going to need the prefixes to go ahead and name these. So give us a shot and then come back to the answer. Okay, so ideally this is what you guys should have got. I hope you can read these. So dinitrogen pentoxide was number 1. 2 nitrogen, 5 oxygen. And then note, depending on who you're talking to, we dropped the A in the pentoxide because it's not pentaoxide, it's pentoxide. Sulfur, hexafluoride. We've got phosphorus, pentachloride. Again, all of these ones with the mono first, we can drop the mono. We don't have to specify it if it's the first element in the compound. We've got iodine, heptafluoride, carbon monoxide. Monoxide here, it is the second element in the compound, so we do have to specify that there's only one of them, and that's with mono. And then we have sulfur trioxide that we have to talk about before we can start the activity, and that has to do with acids. So have we talked about acids yet? No. Okay, so acids are special, and that's why they have their own special little nomenclature. Okay, so acids are things that are molecular compounds, so things like HCl, right? How do you know this is a molecular compound as opposed to an ionic compound? It's composed of 2 or more nonmetals, right? So H and Cl, those are both nonmetals. But from these types of molecular compounds, these acids, when you put them in water, instead of being cool and molecular, they actually act as if they were ionic. So they break apart into these little ions, okay? So again, what are acids? They're molecular compounds that when you put them in water, behave as if they were ionic compounds, okay? How do we denote that this is in water? So we use this little physical state, AQ, which stands for aqueous, okay? This means that this is being dissolved in water, okay? How do you know you have an acid? It's usually denoted by there being a hydrogen up front. Okay, so if you have a chemical formula, there's a hydrogen up front, and you are followed by an AQ, you know you have an acid, and you need to utilize the acid nomenclature rules. Okay, so what are those acid nomenclature rules? So we have 2 of them, depending on the type of acid we are dealing with. So the first type of acid we call binary acids. This again is going to be an H plus some other type of element. Okay, and then the second types of acids are called oxyacids. Again, they're going to be a hydrogen, but what do you think they're going to be bound to? We call them oxyacids. Probably a polyatomic ion, an oxyanion, okay? So binary acids versus oxyacids, we have 2 different rules depending on what we're dealing with, okay? So we're going to start with the binary acids first. So these binary acids are going to be things like HBr, HCl, etc. Okay, they're going to be hydrogen bound to only one other type of nonmetal. Okay, and so how we name these is we're going to identify first off that it's an acid, but we're also going to identify that it's a binary acid. So we're going to use this little prefix hydro first, then we're going to write the base name of the nonmetal that the H is bound to, and we're going to end it in IC, and we're going to put a space, and we're going to write acid. Okay, so for example, this guy is a binary acid, HF. The first thing we're going to do is write hydro, because it's binary acid, and then what is the base name of this nonmetal that it's bound to? Fluor, right? So hydro, then I'll write fluor, and then what am I going to end it with? Ic. So hydrofluoric space acid, okay? Same thing for this guy. Another binary acid, so I write hydro, I use that prefix, hydro. What is the base name of this one? It's an I. Iode, hydro, iode, and I'm going to end it in IC, hydroiodic acid, okay? Okay, so anytime it's a hydrogen with just one other type of nonmetal, you're going to use these rules. It has the hydro prefix, you end the base name with the ic, and you write acid, okay? Now, the last rule is for naming oxyacids, okay? Again, these are going to be acids that contain a polyatomic ion. So this is going to be things like HNO3 and H₂SO4, etc. Okay, these are acids of polyatomic ions. Okay, so how are we going to name these? Number one, we never use the hydro. The hydro is only for binary. Okay, so never put hydro in front of any type of nomenclature with respect to these oxyacids. Number two, the name of it is essentially going to depend on whatever name we have for the oxy anion. Okay, so for example, if we had this guy, this is H₂O₃, what is the name of this polyatomic ion? So this is nitrate, so this ends in 8, okay? So if you have an acid with a polyatomic ion that ends in 8, we're going to end it in ic, okay? So because of this, this becomes nitric and then acid, no hydro, okay? On the other hand, if we had something like this, HNO2, this is nitrite, right? So this is the acid of nitrite. If the polyatomic ion ends in ite, we're going to end it in OUS instead, okay? So if the polyatomic ion ends in 8, we end it in ic. The polyatomic ion ends in ite, we end it in OUS. So for this guy, it would be nitrous acid, okay? So no prefix, just the base name of the polyatomic ion, end it in ic if it ended in 8, end it in OUS if it ended in ite. And then one last thing, I'm going to go and let you guys get started. How do we go in reverse with respect to these acids, right? What if I gave you the name sulfuric acid? How would you know what the actual chemical formula is for that? So number one, does it have hydro? No. So what does that tell you already? It's a polyatomic ion acid, okay? Number two, it ends in ic. So what does my polyatomic ion have to end in? 8, right? So I know this is the base of sulfuric or whatever, so this has to be SO4 2- because this is sulfate. And now if I wanted the chemical formula for this acid, what else do I have to keep in mind? The charge on the proton. H's always have a plus charge. When I combine these two to get the chemical formula, I have to combine them so I have a charge neutral species, right? So how many H's do I need to balance the 2- of the sulfate? 2. So if I was going from the name of the acid to the chemical formula, I have to keep those things in mind, and the chemical formula for this would be H₂SO4, okay? What about hydrochloric? What is that telling me? Hydro? It's a binary one. What is the anion that I'm dealing with? Chlorine. So I know it's a Cl- because, again, that's a predictable charge. How would I balance this with my H+? Just 1-to-1, right? So again, given the name, how do you get the formula? You break it down for each individual rule, and then you balance it with respect to charge, okay? Okay, and so then we've got this nice little flow chart that kind of highlights all of the various tracks with respect to ionic or inorganic nomenclature, right? So we dealt with ionic, depends on the type of metal that we're dealing with. We dealt with molecular, and now we've just talked about acids, and again, acids branch depending on whether or not they're the binary acids or they're the acids of oxyanions, of polyatomic ions. So I would suggest that you guys consult back with this if you need it, but it does kind of highlight things nice and well. And then at the end here, we've got kind of like everything combined together, right? So we give you guys the chemical formula, and we're wanting you to provide us the correct name for the compound. Again, this is going to be all different types of things. So this is going to be ionic compounds, it's going to be molecular compounds, it's going to be acids, and it's kind of up to you to figure out what type of compound you're dealing with, and then how you're going to appropriately name it because of that. Okay, so pause this video, go ahead and go over these, and then come back for the answers when you are ready. Okay, and so these are the correct answers. Again, for number 1, strontium is in column 2. It is a predictable metal, so this is one of our type II ionic compounds. We don't have to specify the charge of the metal, so this is just strontium chloride. 10, on the other hand, is an unpredictable metal. It is a type II ionic compound. So we do have to specify the charge on 10. Again, how do we know that? Well, oxygen has a 2 minus. There are 2 of them, of these 2 minus charges. So that 110 has to balance that. So we have to have a positive 4, which again, Roman numerals is IV. Then we move on to P2S5. Both of these guys are nonmetals, so this is a molecular compound. I have to specify how many I have of each thing. There are 2 phosphoruses, so we have diphosphorus, and then we have 5 sulfurs. We have pentasulfide. We have here an acid. I know this is an acid because it has the AQ designation. Physical state. This is an acid of a polyatomic ion. So this guy, SO3, 2 minus is sulfite. So my polyatomic ion ends in ite, therefore my acid is going to end in OUS. We don't use hydro, it's just sulfurous acid. Potassium is a type 1 metal. We don't have to specify its charge. It's got a -1 charge. This guy, ClO₂, is a polyatomic ion. Again, this is one of our oxyanions. This is chlorite. It also has a 1- charge. Then we have another type 2 metal. We have lead. Lead is unpredictable, so we have to specify its charge. So 2- is sulfate. SO4 is sulfate. It has a 2- charge. Therefore, lead has to have the 2+ charge. Again, we have another molecular compound. This is 2 iodines, 5 oxygens. This is diiodide pentoxide. And then finally, we have another acid. This is a binary acid. It is an acid of just one other type of element. That element is iodine, right? So we're going to use that hydro prefix. So this becomes hydroiode, and then ic, hydroiodic, and then acid.